Okay, so let's talk about torque. So remember, it's a new physical quantity. The unit is Newton meters, and sometimes you can think of that as a twisting force, right? So it means it's the physical quantity that can rotate about a fulcrum, an axis of rotation. And the definition of it is the distance between the axis of rotation and the point where the force is applied. So that distance here times the component which is perpendicular, right? So, for example, in that case here, you want to use only the perpendicular component because the x component is not helping in twisting about the axis of rotation. We already talked about that. What do you want? Can you sit over there and only equation sheet and your calculator? Sorry, I'm just very tired. Okay, be patient with me. Can you? Yeah. Okay, only equation sheet, calculator, and scrap paper. Sorry. Okay. So, for example, in that case, the torque produced, you can have your scrap paper, calculator, and equation sheet. The torque will be equals to 0. Okay? And now we go to an equation about that. So for the pop quiz, I think you have bonuses. I think I gave bonus point. I forgot. So if I didn't, I will do it next time. But for the pop quiz, you see, I have updated my slides. So make sure you have the right slides, right, from Dropbox. Don't use the previous slide where I give a lot of information there, right? So if you are going into the medical field, all the human body is about joints, which are fulcrum, muscles, which are effort or force, and load. So load could be a dumbbell, it could be your own mass, it will be the mass of your arm, the mass of your leg, and so forth and so on. So it's very interesting physics, applied physics here. Okay, and then we go to equilibrium. So remember, when we talked about forces, the way I was teaching you is that something is in equilibrium. So first you have to do the free body diagram and you want to show the components of the forces, right? And then there is equilibrium so far. If the system cannot rotate about an axis, then we will say that everything to the right equals everything to the left. And then you take only magnitude, or you say everything up equals everything down. Okay, so that's one way to do it. In your textbook, they will say the sum of the x component equals 0, the sum of the y component equals 0, but the same thing. Now, for a system where when the system can rotate about a fulcrum, like in the human body, like your hip, for example, like if I don't have muscles, I can go like boom on one side. So in that case, you have to involve torques. And there is equilibrium if you have the sum of the clockwise torque, it's all in magnitude, equals the sum of the counterclockwise. So it means the torque that wants to make the rotation clockwise should be equal to the sum of all the torques that wants to make the rotation counterclockwise. So let's start with a very simple system. So you have, I think this is 1 kilogram. We already solved that system, but I just want to show you the methodology. Right? Even if it's easy, I'm not looking for the answer. I just want to show you the methodology to follow. So first step in your methodology, you want to make a drawing. of the situation. So you have somewhere you're going to put your fulcrum, okay, and you're going to have all the forces acting on the system. So your meter stick here is the system. So here you have a large force. I think this is 1 kilogram. This is 500 grams, which will be 0.5 gram. And obviously, you can see that that distance here should be twice that distance there. So you don't need to take physics to understand that. It's from your guts, but I want to show you the methodology. So this distance here is 10 centimeters, and it's given. I'm going to call that R1. Okay, so the distance between the application of the force and the fulcrum, and I'm going to call that R2. Okay, so I'm going to use that statement of that equation, okay, because there is an equilibrium. There is no winner, okay? And when you use this, it doesn't matter which unit you are using. It means if this is in kilogram, you can leave it in kilogram as long as you have kilograms on both sides. If the distance is in centimeters, you can leave it in centimeters as long as it's in centimeters on both sides because of the equal sign. If that disturbs you, be my guess, you can convert kilogram to Newton and you can convert centimeters to meters. But as long as you are consistent, you don't have to. Okay, so this is your fulcrum here. So in that case, so what's the definition of torque? Produced by a force about a fulcrum. Again, it's the distance to between the fulcrum and where the force is applied times the perpendicular component. Okay, we already done that. Okay, so now I'm going to use this. Okay, I'm just want to show you the methodology. So the sum of the clockwise torque will be equal to the sum of the counterclockwise. So this force wants to make what? Clockwise or counterclockwise? You all agree? It wants to make it go this way. And this one says, no, 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 you don't. That will be counterclockwise. So on one side, I'm going to have F2, which is already perpendicular, so I don't have to worry, times R2 equals, counterclockwise will be F1 times R1. So I'm just showing you the steps. Now, of course, when you look at, if you are asked for a question for the test, find the torque, then yes, you have to convert. That means the distance has to be in meters, the force has to be in Newton, and the torque has to be Newton meters, right? And of course, a force can be a weight, and the weight is mg. So that will be kilogram. That's the acceleration due to gravity. So that's going to be Newton. So that's how you convert kilogram to Newton. But in the case of an equilibrium, you don't need to convert. So F2, I'm going to stay, you can keep that in kilogram. Okay, because anyway, you see the kilogram is proportional to the Newton. So it doesn't matter. It's like you multiply by 10 everywhere. I'm going to keep that in centimeters as long as you are consistent both sides. Agree? So F2, in that case, so it was given as 500 grams, but I cannot keep 500 grams because on the other side you have kilograms. I have to be consistent. Both sides need to have the same unit. Okay? So 500 grams is just 0.5 divided by 1,000 times, that's the distance in centimeters, okay, equals the force here. Oh, I did the opposite, right? No, it's right. No, it's right. So clockwise, it's the opposite. Okay, here, right? So F2 will be what? 1 kilogram No, I said when there is an equilibrium, you don't need to convert. No, only if you are asked to find the torque, so then you have to convert. You want to make sure to have distance in meters and the force in Newton. So if you have kilogram, you multiply by 10, you get Newton. But in that case, for an equilibrium, as long as you are consistent on both sides, you don't need to convert, right? Yes? Okay. So you have something is wrong. I am so hot. It's hot. No? 1 times 10 equals counterclockwise. F1 is 0.5. Is that right? Times 10. 5. Like, did I do a mistake? I don't know what yes, I'm trying to find R2. So R2 will just. Oh, okay. Okay, so let's, thank you. So clockwise is 1 times R2 equals 0.5 times 10. Okay, so that's good. So what do I get? 5 centimeters. So when we are dealing with an equilibrium, we don't need to convert as long as we have the same units on both sides. Because if you were to find Newton, you will be multiplying by 10 on one side and by 10 on the other side. So it's like you have a balance here, like, scale, a balance, like a scale. And you put 5 kilogram on one side. If you put 5 kilogram on the other side, you're not changing the equilibrium. Agree? Like that's if you have a scale like in the old time, if you add the same amount on both sides, it's not going to change. So that's the way you want to do it. Okay? So that's how I know we are a little bit ahead, which is very good because usually I have this slide around Halloween, but it's very close. Okay, so try to do this one. So the first thing you want to do is to label everything. Okay, 5 Newton and extinguishes balance. The 5 Newton is based 20 centimeters. So this is 20 centimeters. Okay, you help me make sure that I'm not doing mistake. Is placed 20. Okay. Okay, we're gonna skip A for now. I want to go to B. So that will be R1. That will be F1. And somewhere farther away, it has to be farther away. You're gonna have R2. And it's gonna be F2. Okay, so we have R2 F2 equals R1 F1. So that will be clockwise, that will be counterclockwise. So clockwise, counterclockwise. Okay, agree? Okay, so R2, that's my unknown, times 3 equals 20 times 5. And you don't need to convert as long as you have, your answer will be in centimeters. So R2 will be, yes, 33 about. Okay? Do you agree? Yeah. Any question? Yes.
So does it matter between label as F1 and F2?
No, it doesn't matter. Okay, as long as on one side you're going to have F1, R1, the other side F2, R2. But, so let's go back to A. So here they say, what is the torque produced? So in that case, yes, the units matter. So the torque produced by the 5 Newton, which I called F1, about the axis of rotation is, so the force times R1, and here I want to make sure to have the right units, because it's not an equilibrium, you're just asking you to find the torque. So F1 is 5, which is what? 1 Newton meters. And let's see, it's if you want to do it the right way, clockwise is negative by convention. Okay, I won't be after you about the sign, but if you want to do it properly, maybe you are taking the MCAT or whatever, maybe it's important. So it will be actually it's 1 Newton meters. So why do you need a sign? Because actually torques are actually vectors. So if the rotation wants to be this way, that will be the vector torque. And if the rotation wants to be that way, that will be the vector torque. So you see they cancel each other. But that's for more advanced physics. A torque is actually a vector. So if a torque is trying to make something spin in this direction, the thumb is going to be the vector torque. It takes you to something called cross product. It's when you multiply, you cross two vectors to have a third one, but that will be calculus 3 or 4. So anyway, for our purpose, we're going to say clockwise is negative, counterclockwise is going to be positive. Okay. And here I say textbook. So textbook will be referring to the one that is recommended by the department, but or the book Johnson and Cotnell, that's the one I'm using for my slides. So this comes from my head, but the other slides will come from the Johnson and Cotnell. But if you have the other book from the department, it's very good as well. And here is a problem I'm recommending to make sure you open the textbook. Textbook have to be open. That's the goal of a textbook, is to be open. Okay, so now when you have an equilibrium, so for example, in that case, you see you have, so here we suppose the plank has no weight, right? Let's say we neglect its weight. Mm-hmm. You're going to have, you hold the plank here, so you have a force up, and the weight of the little boy down. So not only do I have everything up equals everything down, which means F1 plus F2 equals mg. So that will be one equation. In addition to that, I can apply the torque equation, and it doesn't matter where you take your fulcrum. So you can take the fulcrum here. So let's verify just for a conceptual question. If I take the fulcrum here, you see, it can rotate this way. What's the torque produced by F1? Is F1 apply any torque? Can it make it rotate, make it twist? Mm-hmm. No. So the torque will be 0. Why is that? Because it's F1 R1 and R1 equals 0. Or you just use your common sense. If the fulcrum is here, F1 doesn't help at all. And then you have a torque here, but that's trying to make it clockwise, and this one is making counterclockwise. So if I apply equilibrium about the fulcrum here, what do I get? Okay, let's write it down. A little bit of algebra is very healthy for the day. Okay, so what is the torque that will produce clockwise? What's the force here? The weight, very good, right? So it's going to be mg times the distance between the fulcrum and where the force is applied, and the distance is 3L over 4, equals, and this guy is holding it, he wants to make it counterclockwise if you let it do it, so it will be F2. And what's the distance? 1L. Okay? You can even do boom, boom. So you see that F2 will be 3/4 of mg. So that's, we rarely do those. This is algebraic expressions, but it's good to understand how it works. Now I can also say everything up. So we review the last unit equals everything down. So up, what do we have up? What is pushing up? Very good. F1 plus F2 equals mg. Okay? And you can even say F1 plus 3/4 mg equals mg. And 1 minus 1/4 is 1 minus 3/4 is 1/4. Very good. Okay, so it's not that it's advanced. It's a little bit of algebra. Usually students don't like it because they like to plug numbers, but sometimes it's not that bad. So that means this one is 1/4. So she has it easier because she's the effort here is farther away than him. Okay. Okay, so this way. So this problem, I just want to show you how it works. You see that, what do you think this is? Very good. So any plank or any object has a center of mass, right? So it's an introduction up to the center of mass. So if you have, no, I can tell you like a demo you can do. I will tell you if you're looking for a demo. So anyway, this is about homogeneous. So you see, I can try to balance it out. It should be just at the center, like this. Okay. You saw it, right? It was at the center because it's homogeneous. So what is the center of mass? It's the point where the weight is pulling down. Okay, so the center of mass is that point where weight is applied. So if it's all homogeneous, right, it's going to be at the center and it's imbalanced because the fulcrum is here. The weight is going through the fulcrum and there is no torque. Now if I can do it this way also. As long as the mass is the same on both sides, that here will be the center of mass. Does it make sense? Right? And the center of mass is defined through the torques, right? So that's the point where there won't be any torques applied. Okay, because this one wants to rotate clockwise, this one counterclockwise, so it doesn't move, and the weight is going down through the fulcrum. So when the force is going through the fulcrum, there is no torque. So if I have a system like this, so that could be, for example, the sun and the earth and the moon are two stars. The stars likes to be in binary system. They don't like to be single. And you see that will be the center of mass. You see that? Right? Mm-hmm. And I can say M1 R1 equals M2 R2. That's the definition of the center of mass. Everything happens like the weight is applied here at the center of mass. That's how, oh, my arms. It's terrible. So that's how you define the center of mass, right? So in uh, in anatomy, it's very important to understand center of mass. Okay, so for example, here you have for men and women, it won't be the same. So the women have a lower center of mass than men, but the idea is that everything happens like the weight is applied here at the center of mass. That's why I will show you a video, but women can do things that men can't. Like we can be on the wall and touch our feet, and men can't, because of that center of mass business. Because if you want to have stability, your center of mass has to be always above your feet. If it's not, you lose stability. You can manipulate your center of mass. So people doing yoga are excellent with that. You see, you can do those exercises. So now the center of mass has been moved. Okay, it's not inside the body anymore, but the center of mass has to be above the feet. If the center of mass moves too much forward, you're going to fall. So that's why the Tower of Pisa, for example, even though it's a lean Tower of Pisa, it's not going to fall because its center of mass is still above its base. So that's, we'll get back to center of mass. Here's another example. Interesting. So that's the plank. Okay, so you see, that will be the center of mass, a little bit higher up. And everything happens like the weight is applied to the center of mass down. So in that case, we call that the load. It's a load because you don't need any weight to work out. You use your own load. So I don't know what's the discipline, but there is a whole thing where you don't need prop, right? To exercise, you use your own weight. Yes, what's it called? Exactly. So no weight, no nothing. You just use your own weight, right? So you have here the normal force from the ground and the normal force from the ground. So you can use down equals this force plus that force, and then you can take the fulcrum over there, for example, and you have the torque produced by the weight should be equal to the torque produced by the normal force. So that's how it works. Isn't that interesting? Mm. So like exercise science, physical therapy, it's great because we damage our body so much with the computers. Like all day long, I am on the computer, which is very bad for the low back. So you will always be with some work. And as I told you, you see women tend to damage their knees more often because you see how it makes an angle there, right? So if you don't have enough muscles, it's very, very easy to be unstable, like chung, and then you damage your meniscus. Where men, it's not the same, right? Because it's straight down. So let's go back to the center of mass and talk about that. A little story here. So if you have a plank like this, right, and it's all homogeneous. Oh yeah, let me show you the demo. A very easy demo. So you have a broom. to sweep the floor, right? So one side we have a lot of weight, right? And then you have the stick. You put your two fingers on both ends, and very, very slowly, you're going to bring them toward each other. Very, very slowly. And you're going to see that where you end up, that will be the center of mass. And it will be in equilibrium. For a few points, you can do that. Very easy. You can do the same thing with a baseball bat. Okay, take your baseball bat and have more mass, less mass. You bring your finger very, 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 very slowly. Where you end up, it will be balanced and it's going to be the center of mass. So if you're interested, if you go on Google, not on Google, on YouTube, you find many demonstrations with the center of mass. Especially if you are in exercise or yoga. Yoga, there is a position, I don't know if I remember. It's called the crow something, I don't know. I will find it. I don't want to take too much tangent. The physics of crowbar. Do you see that somewhere? The physics of crowbar issue here. Yeah, but where is it? Like that's the file, but I need the website. Must be the physics of crow pose.
Second row.
Oh, thank you. So, okay, the physics of crowbar has okay, this is. So you see here, extra credit. Apparently it's easy to do. Okay, I didn't work for me, but apparently it's easy to do. And the idea is that you do it slowly and your center of mass will be somewhere there because you are a little bit forward. So your center of mass will be here and it has to be just above your hands if you want to be stable, right? And if you do that, you will be in equilibrium. A student told me that it's easy to do. And then here you have another demo that you can do if you're interested. And it's all about, so people doing with yoga can manipulate that center of mass. But the idea is that the center of mass has to be always above the feet or above the hands. Otherwise, you're going to fall. So if you go on Google, you can see the steps. You start slowly and then, I don't know, it seems like you need to have muscles in the arm. It seems to me, but if you can do it, good for you. I'll give you extra credit. Right, so here, that's the baseball one. Okay, you start from two hands, you bring your hands very, very slowly, and you will end up at the center of gravity. Here is another demonstration you can do. Okay, you see here, it works. It will be stable because that will be here, the fulcrum. Why it doesn't fall? Because the center of mass will be just underneath the fulcrum. And there will be no torque. So it will be in equilibrium. Right? So, okay. How is he doing it? Because that doesn't make sense for the physics.
Yeah, doesn't
He what?
anchor his shoes?
Yes. He anchored his shoes. So he was a genius, right? This guy was a genius. He made like special shoes, and he anchored them. Like there was a hook.
That's lit.
Yes,
Yeah.
yes. Because otherwise it doesn't make sense, right? Because the center of gravity is here and it's not above the feet. So I used to have the joke, but I cannot, that was 20 years ago, you cannot do it anymore, but it says, blank gravity, I am Michael Jackson. So I cannot say it anymore. So, but that's how you do it. I'm going to try again, but I'm not very hopeful. But okay, so that was about center of mass. So in that case, so you have a plank, and you see here the center of mass will be just at the center. And if you put your fulcrum here, it will be balanced. Why? Again, why? Because the weight will be down here, going through the fulcrum, so there is no torque. You get it? Mm-hmm. So now let's say you take the same plank like this, right? And now you have, so the center of mass is still here. So that will be your center of mass. But now you put your fulcrum here. So what's going to happen? You have the weight here. Okay, so of course it's going to be tilting one way. Now, if you have a little boy here walking, so here it will be tilted this way. But as he walk, there will be a place there where he will be just in equilibrium. So we can call that R1. That's going to be R2. Yes? Mm-hmm. So you're going to have R2, the weight of the plank, equals R1, the weight of the little boy. Do you understand? Mm-hmm. So you can do an experiment, come up with an experiment with that. But that's the idea here. You see, you have the weight of the plank. That will be the fulcrum. As long as the little boy is here, there is no problem. The winner will be on that side, about the fulcrum. And then there is a place where it's going to tilt down. And because it was Halloween, and I said this is like a deadly grass that eat little boys for some reason, right? So it will not be in equilibrium. So I'm going to save this one for next pop quiz. Okay, I will make it more clear. Okay, so we're going to try to do this one. So a lot of torques and levers in the human body. So here is an example. Any joint that you have in the body is actually a fulcrum. And then you have the load. So in that case, that will be your body weight. And then you have here the muscles that keep you up straight. Otherwise, you're going to be, as you get older, you start to have weaker bone. It's always weaker muscles, always happening on one side and not the other side. So you start to tilt this way, or you tilt that way, or you tilt that way, right? So it's all about equilibrium. So let's try to do this one. You can help each other, talk to each other. It's an equilibrium. And you see, these are all the forces acting on the lower arm. So you have the load here from the book, the physics book. Oh, it says physics. Okay, very good. And then here you have the center of mass of your lower arm, which is not at the center because you have more bones there that you have there. And then here you have the muscles from the bicep. And then here at the joint, which is, remember, fulcrum are joints, you have the normal force, right? Or you have the weight of pushing down. But we don't care because we take the fulcrum there, right? So there is a force applied to a fulcrum. It doesn't twist anything. Okay, go for it. I try to do that because I know some of you wants to go into the medical field. Exercising is very good because you are oxidizing, you are transferring electrons. Okay, so the fulcrum, I'm going to take it here. So I like to make it like a triangle. So then you have to imagine that this is like a lever, like a plank, right? And each of those forces are going to produce a torque. This one is trying to make it very good clockwise. This one has to make it clockwise also, right? So the best way, you take your arm, you're not sure, and you play. And this one, very good. So that means the muscle has to work against the weight of your arm and also the load. So it's very hard to exercise with the lower arm because the lower arm is meant to increase the distance, not to multiply the force. So it's very easy to break as well. That's why we have a very light bone, okay? Because it's to make it easier. So, but it's also very easy to break. So anyway, let's do that. The sum of the let's say counterclockwise has to be equals to the sum of the clockwise. You don't need to convert. Here we have kilograms. We can take everything in kilograms. And then if we want Newton, you just have to multiply by 10. You have centimeters. You can keep everything in centimeters. Okay? So try to do that. So it's always force times distance and force times distance and force times distance. That's all. So try to do it. You can help each other. Okay, so clockwise, counterclockwise, you see you have the force. That's what I'm trying to find. So the force produced by the bicep times the distance of the fulcrum. So 4 equals clockwise. You have the weight of your arm, which is 2.5. So 2.5 times 16 plus the weight of the load, which is 4 times 38. Okay, so it's not 48 or 46. 38. I said 36 here, but it's 38. Is that clear? Mm-hmm. So you're right. You at the end we're gonna multiply by 10. So as long as I have kilogram, that will be like a force in kilograms. Right, but you're right. Kilogram for muscles won't make any sense, so we're going to convert it in Newton. But if you have kilogram, we're going to get kilogram, and then you convert to Newton. And tell me what you get, because I made a mistake. So you divide, so you do 2.5 times 16, enter, plus 4 times 38, enter, and then you divide by 4. 48? Yeah. So 48 kilograms. But in Newton, 480 Newton, which is in pounds. If you want to find in pounds, you divide by 5, about. Divide by 5. Yeah, 96. 96? 96 pounds. About, so 96. It makes sense, no? For a muscle, 96 pounds. Like 40 pounds, not that bad. 96 pounds. So anyway. Okay, so that's, I changed the assignment. So assignment for talks has no tutorial because I made it easier. And, but there is one that's part of your assignment. So even though you have no tutorial, I'm going to do it with you. So why don't you try to do it? You decide of the fulcrum. The fulcrum is in the human body. Usually it's the joint. We have a lot of joints. And you have tendon, attached to the joint, attached to the muscles. Okay, so the only difficulty you have is reading comprehension and then drawing the forces properly. So you can try to do it. Okay, so lower arm has a mass 3 kilogram, 12 centimeters. So this is my fulcrum here. So it's a bicep extension. He's doing something like this. Bicep extension. So 30 centimeter and then 3 kilograms at the center of gravity, 12 centimeters. So here we have, so this is 12 centimeter and you have the weight of the arm, which is, so this one is 8, this one is 3 kilo, right? 3 kilogram. And the load is 8, right? Mm-hmm. And force the muscle. So you have the muscle here. That's your muscle, and you have the distance here. Agree? So the first step, you decide of a fulcrum, and then you put all the forces. And you see this one wants to do a clockwise, this one wants to do a clockwise, and this one, yes, counterclockwise. So why is it hard? Because not only you have to have up equals down, but you also have torques involved, right? You want to prevent the torque to happen. Okay, so you have the sum of the counterclockwise equals the sum of the clockwise. Agree? Any question? So you have F times, I'm going to do in kilograms first. So 2.5 centimeters equals 3 times 12 plus 8 times 30. Okay, so remember pandas. If you do that, you don't need parentheses because it's always multiplying before it adds. What do you get? 1. I found 110, no? 110 kilogram. But if you want to turn that into Newton, so you multiply by 10 Newton. And if you divide by 5, that's going to be 2. 20 pounds. You will have to ask ChatGPT if it makes sense, that much muscles. I don't know. Anyone is in working out? Can you deliver that much force?
A lot.
That seems a lot, no? I have no idea. Okay, I don't know. Looks like 200 pounds is a lot, but I don't know. I need to ask. Okay, dumbbell. Yeah. Okay, little bit more. It's very bad for your joint. Okay, you need to have a lot of muscles to do that. But you have again the joint here, so that will be the fulcrum. You do have forces acting on that joint. You always have forces acting on your joint, but it doesn't matter if you are using torques, because any force pushing on the axis of rotation cannot make a twist. So the torque will be equals to 0. Do you agree? So that comes from the book Johnson and Cudnell. And you have the weight of the dumbbell, which is the load, and you have the weight of the arm, right? And then the muscle, so that will be the deltoid. I would say the bicep, but apparently no, it's not the bicep. And it's, you see, it's at an angle here. Thank you, thank you. So you see that muscle is at an angle. So remember, to find the torque, you need to find the perpendicular component. Right? Because the force has two components going from the tail to the head. You have the X component that just is going to damage your shoulder if you don't pay attention because it's pushing the arm in. And the Y component is lifting up. Okay, so you can try to do this one. Usually it's a sign that you have to use. So in that case, yes, it's a sign. And again, it comes from the book, Johnson and Cudnell. Okay, so don't wait for me to do it, right? So that way, when you do the homework, it's going to be piece of cake. So the axis is here. You see that force here has two components. That's the component we want. It's the perpendicular component. That's the one that is helping lifting. You have a component going this way, but it's not helping. It's pushing the arm in the shoulder joint, so it doesn't help at all. And then what else? The arm, So this is 31 Newton. This is 1840 Newton. I'm going to convert to centimeters because it is easier. Not to deal with the zeros, but you can keep this way. So if you use centimeters, you multiply by 100, but you don't have to, okay? So that will be clockwise, and that will be clockwise, and that will be counterclockwise. So the sum of the counterclockwise equals to the sum of the clockwise. Okay? Do it, don't stare. So counterclockwise, you're gonna have the component, perpendicular component. Okay, so it's gonna be, no, I made a mistake, right? Thank you. Yes, you're right. I made a mistake. So this is 840. This is 840, you're right. 840 is here. And this is your unknown. So you see, make sure you read the question several times. Okay, so you're right. So that will be 1840 sine what? 13 times the distance. I'm going to put centimeter to simplify my life, but you don't have to because it's 15 centimeter equals clockwise. That will be 31 times 28 plus, I don't know, times 62. Is that right? Okay. And I need to solve. You can keep in meters if you want. This is just for me. I didn't want to have the decimal, but you can. So 1840 times sine 13 times 15. I put in centimeters. Okay, enter minus 31 times 28, enter, divide by 62, 86. Did you get 86? Okay, so no, it should be 86, even if you, okay. Okay, so 86 Newton, if you want, is the equivalent of 86 kilowatt. But 86 Newton. Okay? And 86, which is about, I don't know, 20 pounds. That make more sense than 200 pounds. I don't know. I have to find out by SEP the force in pounds. Any question? Do you agree? Okay. Okay, so in that case, what is the only one that will be in equilibrium? C? Yes, because the other one, like for example, okay, this one is 2F and FF, so right equals left, but about the axis of rotation, it will make a rotation happen. So this is called static equilibrium, is when up equals down, right equals left, and the torques balance each other out.
Because the two bottom ones, they're both trying to twist it, right?
Yeah.
Then 2F is twisting it in the other direction.
Yeah, so for the twisting, you are right, but it won't be in equilibrium for up equals down. Because you have up equals down, okay, but this 2F is not balanced out by a left one. So if you want the total equilibrium, you need to have a 2F to the left. So it will, even though it doesn't twist, it will be translated. Yes. Yes. Okay. So this one is showing you how to combine the two equations, right? Up equals down and then the torques. So here you have the weight of the lady there. So we're going to neglect the weight of the plank. And then you have the fulcrum. So you have the normal force pushing up. And then you have from the bolt pulling down. So you have a huge normal force from the fulcrum because it has to balance out the weight of the lady and the weight, not the weight, but the bolt here. That it's attached here and it's down. Okay, so we're gonna put the fulcrum here to begin with, and we can find F2. Okay, so find F2 and you take the fulcrum there. So it's a typical problem because you can combine the three set of equations. Right equals left, up equals down, the sum of the torques equals 0. So that will be 530 Newton. And I'm going to take the fulcrum here. So that wants to do a clockwise. That wants to do a counterclockwise. Okay? So try to do it on your own. So then like that, you're going to finish the homework. So you see, you still have a force here, but it's pushing on the axis of rotation. So there won't be any twist. Okay, so you have the sum of the clockwise equals the sum of the counterclockwise. So clockwise 5 30 times 3.90 equals F2 times 1.4. And I have meters, so everything is good. So what do you get? 1476 Newton. Do you all agree? So then to find F1, I have two ways to do it. I can change the position of the fulcrum. I can do that. You remember, when there is an equilibrium, I can decide a fulcrum. I can change the position of fulcrum even if it doesn't make sense. Or I'm going to use everything up equals everything down because it's an equilibrium. Okay, so try to use that and find F sub 1. Are we almost done with talks? I think we're going to have test 3 very soon. I think I'm going to aim at the 19. Did I say the 19 before? Yeah. Okay. Okay, so up we have F2. So F2 is up. Down we have 530 and we have F1, but we already have F2. So 146 equals 530 plus F1. So F1 equals. How are you doing it? You don't do it. You spacing out. Yeah. Don't space out.
2.78.
3?
About 3, yeah.
What do you mean 3? 146 minus 530.
Yeah, 2.7. But if you're rounding it up.
2.7? No.
14. Wait, what did you
What are you talking about? So 1476 minus 530.
Hold on, pause.
946.
No, yeah, you're right. Pause.
We are all tired. Especially me. 946 Newton. Agree? Okay. So, they round because they pay attention to the significant values, but remember, we don't worry about them. Chemistry worries about them. Okay, so all that in the Dropbox, you're gonna have the solution. Why don't you try to do number 3? Help each other. Right? Try to do it on your own. Don't space out. Don't fall asleep. Okay, so the only difficulty here is if you stare, nothing will pop out. You need to do, you have to draw. Without drawing, it's extremely hard. You have to draw it. A seesaw. Make a seesaw. George. Okay, we're gonna make a George. Okay, do it. Don't wait for me. So that's George. And then there is Alice. Okay, so this is Alice. And then she's sitting 1 foot. So the distance here is 1 foot. And the whole thing is 12 feet. So this is 12 feet. So that has to be 6. So this one has to be, yes, 5 feet. Okay, so everything is in the drawing. And then the dad, 150 pounds, that's very good for that, 150 pounds. So he has to sit closer, right? Because obviously, 2.6, yes. Okay, so here, that's the dad. 155 pounds. And the distance, I'm going to call that X, yes. Yes, it's 2.6. Okay, but do it. So this one, try to twist clockwise. This one, try to twist clockwise. And this one, try to twist counterclockwise. Nothing happens because they are in static equilibrium. So the sum of the counterclockwise equals the sum of the clockwise. Okay, so that means dad times the distance, I'm going to call that S, okay, X, but X, and X, I'm going to call that, call that Y, equals 5 times 32 plus 6 times 40. 6 times 40 times, yes, 42. 42, right? Do you all agree? Right? So you take your TI and you get 2.6. Do you all agree with that? Okay. So 2.6 feet. Okay? 2.6 feet. So there is a very nice lab. I don't know if you do it, where you have a meter stick and then here you have a fulcrum and you have 2 masses. I think I will do that for the pop quiz. You have M1, M2, and then you have a third mass, like let's say it's a heavy mass, and you find the position so it balances out. So that way you can find the unknown mass, and then you check. Did you do that for the lab? No?
Yeah.
It's cool. Oh, I have it. I forgot. I will bring it next time. Oh, yes, I have it at home. Okay, so center of gravity here. And the center of mass. Okay, let's just I'm gonna give you examples of some cool 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 cool. If I find the video here, so I'm gonna accelerate. So maybe it's gonna inspire you if you want to do some demo, and it's about the center of mass.
Hey, what's up? It's Mr. J with Shine the Fly, and today I have a couple of challenges for you. If you're up to it, video yourself doing these challenges and post them on social media, such as Facebook, Twitter, or Instagram. Make sure you're using the hashtag #ShineTheFly. Are you ready? Let's do this.
So it's about the center of mass and being above your feet, otherwise you're gonna fall.
Now, these challenges are all about gravity and finding your center of mass. The term gravity is used to describe the force of gravitation on an object or near the surface of a celestial body.
Does it go too fast? No?
Such as Earth, the Moon, or some of the planets. Now, this force pulls on all mass. All mass exerts gravitational force, from the smallest subatomic particle to the largest star in the universe. The greater the mass, the greater the gravitational force. Now, for the center of mass, the point of an object with a mass where the weight seems to be concentrated. This point can be a physical object, or it can be a point outside the object as well. In a round object, the equally distributed mass, the center of the sphere, is the center of mass. To find the center of mass in a regular object, well, it's going to take a little bit more work. And in this case, a lot more fun. First challenge is the thumb press. Here's how you do it. First, place a chair against the wall so they cannot slide back. Sit in the chair with your feet flat on the floor in front of the chair. Your feet must not be slanted or angled to the side. Have a partner gently place their thumb on your forehead. Now, try to stand up without forcing the hand back. The reason it's so hard to stand up is because the center of mass is still over the seat of the chair and not over your feet. The next challenge is chairlift. Here's how you do this one. Place a chair along the wall. Now stand so that your feet are not under the chair. Bend over at the waist, place your head on the wall so that your back is flat and parallel to the ground. Now lift the chair and try and stand up.
And that's the boy. He can do it. Isn't that interesting? Because we don't have the same position for the center of
this one may
mass.
vary based on gender. The center of mass for boys is higher than the center of mass for girls. When a boy is bent over, his center of mass is actually over the chair and he's balancing against the wall. When he tries to stand up, he'll fall most of the time. Girl center of mass.
You can try. So to be able to stand up, you want to have the center of mass above your feet. Okay? And if it's too high up, you can't.
Lower close to the hips. When she's been over, her center of mass is still over her feet, so she can most of the time stand up. This next challenge is the quarter grab. Here's how you do this one. Start this one by standing with your feet against the wall. Now place your quarter on the floor at the tips of your feet. With your back, the back of your knee against the wall. Bend over and try to pick up the quarter. Now, the old derriere is the culprit for making this challenge a little bit difficult. When people bend over, their rear ends extend to balance them, which keeps the center of mass over their feet. Against the wall, an individual's rear end cannot counterbalance them. Now, my final challenge to you is the leg raise. Here's how you do this one. Simply stand sideways against the wall, with one shoulder against the wall, with the same side leg against the wall as well. Now, simply try to raise the opposite leg without holding on anything. Left. This is nearly impossible for the same reason as before. Your body simply can't counterbalance the weight distribution. Now I dare you to try some of these on your own or with friends or family. Remember to post pictures or videos.
So the experiment done by with the chair. I remember when I was teaching physical therapy, students in physical therapy, they were always doing this experiment in biomechanics. So it's a very famous experiment. So that will be center of mass, right? So for example, here, so how do you find the center of mass? You use the same equations. So you're going to have M1R1, okay, equals M2R. So here you have the weight of the plank. Here you have your load. That will be the axis of rotation, okay? And that's how you can find the center of mass, and you have a very simple equation for that. Okay, so a center of mass doesn't have to be inside the object. It could be outside, like here, right? So for example, here, when you have two stars here, you have the center of mass that will be in between. But if you have something very heavy, like you have the sun, and here you have Jupiter, so the center of mass will be inside Jupiter. And even though Jupiter is very heavy, it's still gonna wobble, right? Or the sun. Because of Jupiter, the sun will still be wobbling. So it's a story of this, right? Like if you have the sun and you have a planet, you see that the center of mass will be somewhere there. And I can say M2R2 equals M1R1. That's the definition of the center of mass. That's how you find the center of mass. But in the case of the sun, it's so big that it will be inside the sun itself relative to the planet. Nevertheless, because the sun is tugging on the planet is tugging on the sun will wobble. You can even detect a wobble. So I found that I was walking in sunny eyes and I saw this drawing and I thought, okay, that's not bad because look, the center of mass is here and you want to make sure that your center of mass will be just above your feet. That's why you have to stretch out your arm, okay, to counterbalance your rear end. Yes, you have mass 1, mass 2. Center of mass has to be above your feet. If you don't maintain that, you're gonna fall. Okay, so same thing here. It's above her feet. She's gonna balance. So if you can do that, I will give you extra credit. It seems to me very hard. Is very thin as well. Why? Why I can do it? It's kind of the crow pose. It's because the center of mass here, okay, is, so you remember center of mass is higher up for a man, so higher up, and he's just above where the hands are. Okay, so that's how you have stability. So center of mass here, you can say this is the fulcrum. Here you have some load, so load 1. So let's say the center of mass for the legs will be here. So weight 1 times R1 equals weight 2 times R2. Can try that. If you don't pay attention, something like this can happen. You see, because that will be here. You see the fulcrum, the center of mass was not well positioned, so it means they put too much stuff in the rear of the plane, and something like this can happen. And I found the video. I don't know if I can find the video. Since I'm partially blind, can you see the airplane? Yes. Bottom. Where? Where? Oh, ici. Oh, okay, thank you.
Officials at JetBlue say a sudden shift in weight caused an unusual sight at New York's JFK Airport Sunday night. A plane at the passenger gate with a lost its balance and tipped back so far its nose lifted into the air. JetBlue said that happened after passengers started deplaning from a flight that had just arrived from Barbados. Once the plane leveled out again, passengers were able to get off slowly. Airport officials say there were no reported injuries or disruptions to flight operation. The plane was taken out of service.
Imagine you trying to work out.
Inspection. The plane was stopped. They'll go back for the team.
Feel like you could be the one that like weighed down the back of the plane.
Yeah.
That happening in the air.
That's it.
In the air. Do you think it can happen in the air?
There was an
It did?
incident where there was a fire in front of the plane. Everybody ran to the back, and the plane dipped nose and it started to stall.
Really? So what did they do? Did they run on their...
No, everyone
No?
was panicking because of the fire in the front. The plane stalled and it just fell
It fell?
because it was
It
stalling.
crashed?
The nose was too high up, so it just stalled.
Really? You mean it crashed or no? It crashed?
I think it was like back in the 70s. There's
Well,
a whole thing on Smithsonian about it.
that's interesting.
That's important.
At the same time ran, the center of gravity shifted towards the back of the plane and just because the plane was like this.
Yes, yes.
So it can't.
It cannot counterbalance, right?
Oh, yeah.
That's interesting. Wow. Interesting. What's your name again?
Kevin.
Kevin and
Ethan.
Ethan. Kevin.
Let's see if I can find the video.
Yes.
It would be good, yes.
It would be good. It's terrible.
So it turns you see I don't know if some of you are doing a dance like this, like a classic dance, and they seems to hover at the same level. That's because you can manipulate by moving your legs here. You can manipulate your center of mass. So the center of mass will make a projectile motion no matter what, because the center of mass only respond to gravity. So the center of mass will always follow your projectile motion, but you can change the position of your bodies around the center of mass, right? So same thing here. And I just want to conclude with this guy who is very famous, who I forgot the name. He's so famous. But so before him, I mean, I don't know if it's him or another guy. Let's see. This Dick Fosbury. Dick Fosbury. Okay. This guy. Before this guy, everyone, the way they were doing the high jump, they will go like this, right? The head first, right? And then he got the idea for the first time. He was the first guy to do it back. So by doing it,
So you don't want to land on the back.
yes.
If they put in pads, now you can do is land on the back.
Or before they didn't put pads.
So you land this.
Right. So that will be hurting, right? So maybe that's why they put pads after that. But before they will do the head first, right? So he got the idea to do it back because your center of mass is still below the bar, but your body is a ball. Do you understand what I'm saying? Mm-hmm. So that was a big breakthrough. You see, your center of mass is still below the bar. The physics doesn't let you do like higher, but by manipulating your body, you see the body can be higher, but the center of mass will still be below the bar. And the first guy to do that was this person. What's his name? Fosbury. Okay, he did that for the first time, and then he opened a new door, and everyone was doing it after that. Isn't that interesting? And of course, see, I used to have no blank, but I have two blanket now.
You don't have to.
Right. And okay, I see people getting. Almost done. Okay, so we are ready for having test 3 on Thursday. No, on Tuesday. No, not next Tuesday. Did I say next Tuesday?
You said the 19th.
19. Okay, we're aiming at the 19.
Okay.
Like from 7. Yeah, because some people work, so maybe from 8 to 11 or 7, 8 p.m., 7 p.m., 6 p.m., 6 p.m. I don't know if you have, like, we'll discuss next time, okay? So if you can, 6 p.m.